scaling limits of neural networks?
OK, thanks a lot, first of all, to the organizers for the invitation to speak. I know I'm going to forget to do this at the end of the talk. So let me just say it's been an amazing workshop. And I think we should all clap and thank the organizers for putting in the time to actually do it. I've definitely learned a lot. It's been kind of eclectic, so that's been really nice. OK, I want to share with you all something that I've kind of been obsessed with the last couple years. It's some broad set of questions that I call scaling limits of neural networks, though half the people here in this room are experts on a lot of at least special versions of this. So I'm going to try to shout people out, but I might forget, and I apologize. OK, if I can figure out how the clicker works, I'm going to be in good shape. OK, maybe I just use this thing.
I couldn't get it to work yesterday with that.
Right. Well, hold on. I actually didn't plug it into anything. Is there a USB for the clicker?
There's a USB-C to USB.
I see it. I see it. OK, that's going to help a lot. It's going to help a lot. Let's see if that. OK, yes. Excellent. Quit. All right, let's see. OK, success. All right, very good. OK, OK, sometimes I give this talk to people who don't do neural networks, so I go through what a neural network is. But let me skip all that. So let me maybe just tell you, oh, no. Oh, no. OK. There we go. OK, let me just tell you my notation. So for me, I'll mainly be considering just fully connected networks. So capital L is the number of hidden layers. Sigma is my nonlinearity. And then generically, I call the output at an input x, z of x with parameters theta. OK, that's just my notation. OK, and the main thing I want to kind of introduce is what I mean by a scaling limit of a neural network and why I care about such things and why you secretly care about them too, even if you didn't know that you did. OK, so I think one of the facts of life that we've heard a lot of talks about is that in the real world, neural networks have many large parameters. OK, so some of the ones that are cool and fun to think about, so taking the width to be large is the thing we do in practice, also in theory. I'm a little bit obsessed with taking the depth to be large, so a lot of what I say is going to be about the effects of large depth. So I'm kind of, OK, I'm a little strange. I write P for the number of training data points that I have. I learned that from Chaim Sopolinsky, I'll say. So you can blame him. OK, but there's other things, right? The amount of compute you're going to throw at the problem, the input dimension for the problem. There's lots and lots of things that are large in the real world. And kind of the fact of life is that it's hard to take all of them to be large at the same time, because kind of mathematically what happens is the limits as they go to infinity don't commute. And so like at a very high level, the kind of question I'm most interested in is, what are the possible limits of neural networks that exist? Before you can analyze them, you have to at least answer that question. OK, so let me tell you two limits that you've already seen and I think are already kind of interesting but are very special cases of neural networks. So one is linear model, so 0 hidden layers, right? Just z is w1 times x. OK, so here the story I tell myself is like this. I tend to draw pictures. I say, let's imagine that we just have two parameters. This is the input dimension, number of features, and the number of data points that you observe, p. And here you are. You have 1 million data points in a 3 million dimensional space. OK, so you know, what I mean by a scaling limit is something roughly like I want to say both these numbers are large. And I want to say I'm kind of close to this corner, infinity, comma, infinity. OK, so how am I going to make sense of that mathematically? I'm going to take some limits. OK, and I could take a limit like this. I could say, well, I'm bold. I fix the number of samples that I have. I take the input dimension to infinity. And then I take the number of samples to infinity. So you're going to find when you do that you're going to get a well-defined mathematical model. And it's going to be outrageously bad at predicting anything you care about and this actual large but kind of finite size model that you have. OK, this is like having an infinite number of dimensions and only a finite number of samples. That's usually a bad thing, especially if your samples are isotropic. OK, that's very sad. But you could say, what about the other way? OK, you could fix the dimension. You could take more and more samples. And then you could take the dimension to infinity. That's, again, a completely well-defined thing. But the two kind of limits are totally different from each other. And again, this model here has basically nothing to do with this model. This model has basically nothing to do with this model. And you're sort of left with, what am I supposed to do? Well, OK, you all secretly probably know the answer. I just dramatize it because it's the last talk of the workshop. So what you know is that really when you're studying a high-dimensional model, the key thing to know is that everything depends sensitively on the ratio of the number of samples you have to the number of features. OK, that's what happens in isotropic situations. Otherwise, you have to take the effective number of samples. So somehow, like mathematically, you take this corner of your diagram, you have to blow it up in the kind of algebro-geometric sense. You introduce a one variable kind of family of models, which is at infinity, but knows about the ratio of p to n. You ask, what's my ratio at my actual model? And you go off to infinity this way. OK, so the point is you have this one parameter family of models out here. And if you actually were to analytically study this model at infinity, it would be a pretty good surrogate for what you have in finite sizes in practice. OK, but this is already meant to be like example number 1. Limits as p and n go to infinity don't commute. You already know this. And so scaling limits, even for linear models, are like not completely trivial. OK, let alone if you want to do something complicated like Courtney does and want to do optimization and do things compute optimal. OK, I didn't include that in the picture, but you could imagine C. There's another axis, compute time. And OK, so fine. That's like kind of example number 1 in my mind. And then example number 2, so this is a workshop on random matrix theory. I do this example anyway, to be totally honest, but it's especially relevant here. OK, so let's take everybody's favorite, or maybe just mine, Arthur's favorite, I'm not sure, deep linear networks. OK, the sigma's gone, it's just the identity. And the output is just the product of matrices times the input. OK, and let's in fact just think about the simplest possible situation where we're at the start of training. So we just have a product of many random matrices. Okay, products of random matrices are things we've been thinking about forever in the probability and statistics world, also in the math physics world. And very roughly, there are 2 regimes. Right? One is you fix the depth of the product, the number of terms, and you let the size of the matrices go to infinity. This is roughly the free probability world. Right? Everything's maximum entropy. We have nice universality results and so on. And there's kind of, as I say, plus infinity papers in this regime in the sense that you can't actually read them all. So there may as well be plus infinity. OK, very good. But then there's the opposite regime, which is really equally well studied. You fix the size of the matrices, and you let the number of terms in the matrix product grow. OK, this is like the world of the multiplicative ergodic theorem and Lyapunov exponents for these kind of matrix products. It's kind of a whole industry of things, which is very beautiful. And the point is that, and I'll give you a concrete example later, these 2 limits couldn't be more different from each other. This is like a minimum entropy, no universality limit. It's like a maximum entropy universality limit. And what I'll convince you of at least a little bit, and this will come back for neural networks as well, is that really the way to interpolate between them is it turns out that the ratio between the number of matrices and the size of the matrices is kind of the key quantity to study. Okay, so there are some theorems, and some of it is conjectural. But there's a whole kind of one parameter family of scaling limits for products of random matrices, which we don't fully understand, but which are very fun, especially if you can't sleep late at night and you like random matrix theory. OK, so the basic point of the rest of the talk is I want to tell you something about what happens when, for me, these 3 parameters are large: the number of data points, the depth of the network, the width of the network. And I will want to say some things, at least, about what happens if you're not in a deep linear setting. OK, that's kind of what I mean. And again, with the understanding that there are other things I'd like to study. I, too, want to do compute optimal scaling laws. But OK, not all of us can make that happen. So fair enough. OK, so this is kind of my notation. But like, in some sense, the question's more important than the theorems, I think. I want to know, like, how do I take everything to infinity? There was L over n. There was P over n. What else can there be? OK, very good. Yeah. Yeah, so that's yet another potentially large parameter. If you're doing an LLM, Z is high dimensional. There's no doubt. And that thing definitely doesn't commute with the other things going to infinity, indeed. So nothing commutes. So it's like, yeah, it's a paradise or a nightmare or something. OK, very good. So let me just start with something which is embarrassing to present when Arthur is in the audience, but I'm going to present it anyway. OK, because I can't help myself, and I want to be more or less self-contained. So I'm going to do 3 versions of scaling limits. That's kind of my plan. They're going to be progressively more complicated, and therefore harder to understand, but more exciting to me because I was working on them. OK, so scaling limit number 1, this is maybe the oldest of all the scaling limits of neural networks. Okay, I'm just recapitulating the model here so we remember the notation. And I'm telling you how I'm sampling my weights at the start of training almost everywhere. My weights will be IID Gaussians with the appropriate variance. OK, so in this regime, what do we do? So there you are, Arthur. I haven't forgotten you. OK, very good. So OK, you fix the depth of the network. You fix the input dimension. I haven't written that, but you fix the input dimension. You fix the training data set. You basically fix everything in life other than the widths of the hidden layers. And you consider the limit where the widths of all the hidden layers go off to infinity. OK, and so in this world, you basically have 2 kinds of phenomena that happen, which are all really the same phenomenon. Oops, OK, put an extra name in here somehow. So the first thing that happens is at the start of training, the kind of functions you get, the output as a function of the input is complicated at finite width. But in the infinite width limit, you just get a Gaussian process. That's like the starting distribution you have. That's a very old result of Radford-Neal, at least for one-layer networks. And then many people at different levels of masochism have worked this out in various levels of generality. But this is just the tip of the iceberg. Not only do you get Gaussian processes, but really for the purposes of doing at least the regression task on your fixed training data set, okay, with a sufficiently small learning rate, there are some things I don't say because we're in polite company, more or less. Okay, the entire process of optimization is just equivalent to replacing your neural network with a kernel. And the features underlying your kernel are these very beautiful and simple things. And input x gets featurized into the gradient you have at the start of training. So theta of 0 is the initialized value. OK, so that's like an amazing simplification. OK, I think when people first did this, so Arthur did this in rather general settings. There's a really beautiful paper of Simon Dew and some collaborators that did it in a very special one-layer setting. This was kind of a surprise to people that this is possible. And this is amazing because at least in some regimes now we know optimization is going to work. We can relate it to things we understand like kernel methods. But everybody understands that there are limitations to this regime. Okay, so it partially elucidates the success of optimization. But it doesn't allow for feature learning in the precise sense that with all the hypotheses set up exactly the way you want, there exists a data-independent linear model, and you're just using that linear model. That's like my definition of no feature learning. Okay, I don't know if Bruno's still in the audience or if he escaped. Okay, we were haggling about what feature learning means. That's my definition. Okay, but it turns out that if you deviate in any conceivable way, really any way, from the exact kind of NTK setup, you will have feature learning. Okay, so if you study things at finite width, or large depth, or large number of samples, or the learning rate is large, or you do a mean field initialization instead of NTK, there's all these ways to get out of the kind of kernel regime. And it's kind of beautiful, and it just suggests that there are many different kinds of scaling limits you could hope to study, okay, to bring it back to the theme of the talk. And so I'm going to present some work on some of these ways of deviating from the kernel regime. And I'm going to start by talking about what happens when the width is finite, which turns out to be equivalent basically to studying the depth being large in a way I hope to convince you of. Okay, so I'm going to go there. Then I'm going to do large P. And then I'm going to say, oh, I'm sorry, I've run out of time. I can't present the rest. But I don't have slides for the rest anyway, so it's OK. OK, so is it OK? Are there like questions or comments before I kind of continue on? Yeah, I'm trying to be entertaining and chipper and all that, because we're at the end. OK, so let me do it. OK, I was once told, if you've ever heard me give a talk, you know this is my joke. OK, I was once told by my advisor that a good talk has several elements. Has to have a theorem, has to have a calculation, has to have a picture, and a joke. OK, that's the exhaustive list. And the key requirement is that the theorem and the joke have to be different. OK, so there you go. There's my joke. OK, so let me give you the calculation now. So I want to say what happens at finite width. And like I was saying, really finite width and large depth are going to be coupled for me. OK, so I want to do a kind of warm-up random matrix calculation, since it's a random matrix workshop, for these deep linear networks. OK, so I'm slightly simplifying the notation. My L became an L plus 1, or an L plus 1 became an L. I have a product of L matrices. Each matrix is n by n, and I'm just studying things at the start of training. Let me just take all of the entries to be IID Gaussians with the right variance. And just because it's isotropic, I may as well set the norm of x to be 1. OK, so here I am back in my picture with the free probability and ergodic regimes. I have my two large parameters, L and n. And I have maybe the simplest possible random variable that you could hope to study, which is just the size of the output, the norm of the output you get for your fixed input x. And I claim that already you can see the non-commutativity of n and L appearing when you study the distribution of this one random variable. It's like the simplest example that there is. OK, so let's think about it together. Let's first fix the depth, so the number of terms in your matrix product. And let's take the width to infinity. OK, so I claim there's an almost sure answer. OK, so somebody who hasn't heard the talk maybe can tell me what the answer is. So what does this random variable converge to? Yeah.
Just a 1.
Okay, excellent. Okay, you can't fool Arthur, it turns out. So indeed, right, the way I've normalized my matrices, these Gaussian matrices are like isometries on any finite dimensional space. And there's only finitely many of them. And so as you go up, you get the norm of x reproduced. You get 1 almost surely. Okay, very good. Now, okay, a slightly more like unusual question, at least in the random matrix world. Okay, what if I fix the size of my matrices and I let the number of matrices go to infinity? Now what?
0.
Okay, why is it 0? Because 1 was already taken.
There is a theorem by Friedman and diachronics about stochastic recursions.
Great. Okay. So there is that theorem. It's true. Okay, there's lots of ways to say it, but let me channel my inner Mert. Okay. So basically, when you study products of many matrices, the natural thing to do is to take L matrices and raise them to the 1 over L power. That's what keeps things bounded. And then all your singular values, this is a theorem, will be between 0 and 1. That's kind of what happens. So if you don't raise it to the 1 over L power, everything is just going to go to 0 exponentially. Okay, all your singular values go to 0. You get 0, and you see that the two limits just don't commute. And so already in this kind of stupidly simple example, the question is, what is going on? So I'm going to preview the theorems for neural networks in this case by showing you my calculation. So this is the only thing I can fit only on one slide as a complete proof. So I claim that the distribution of this random variable is very simple to write down by hand. Okay, so what do I do? Well, like I tell my students, I write down the definition. You've got to start with the definition, otherwise you're not doing well. And so what do? You use the fact that this thing is like an exact cocycle, if you want to use those words. So you say, well, look, the difficulty is the product, so let me just multiply and divide by the norm of the first kind of w times x. So because w is a Gaussian matrix, the norm of this Gaussian vector is independent of the direction. So these two terms are independent. And moreover, I know the exact distribution of the norm. It's just a scaled chi-squared distribution. Okay, and because this matrix W2 is isotropic, I may as well replace this with my favorite unit vector, which I've called x. Okay, so this is progress, right? I have one fewer matrix in my product, and I keep doing this for every term in the product. And what do I get? I get this kind of beautiful explanation of what this random variable is. It's a product of IID random variables, namely these 1 over n times chi squared with n degrees of freedom with the square root, because I didn't put a square in the norm. But already, if we just pause for 1 second, we see the battle between n and L. Okay, they fight each other. Each of these random variables tries its hardest as n grows to concentrate around its mean, which is 1. However, there's a little fluctuation. Okay, you got to give up the fluctuation. And the more terms you have in the product, the more you exacerbate those fluctuations. That's the basic tension between depth and width. And so if you want to say this a bit more elegantly, you put this in x sum log form. And in the exponent, you just have a sum of IID random variables. And you can apply the CLT when L is large. And what do you find? OK, the mean of each of these logs is on the order of 1 over n. The variance is on the order of 1 over n. And you see that there's kind of this emergent thing. It's not L that was important or n that was important. It was their ratio that was important. OK, so that's kind of a, in some cases, theorem, in some cases, still a conjecture for these matrix products, depending on whether you're thinking about global or local statistics, that really there's a one-parameter family of random matrix products parameterized by this ratio of L over n. And it interpolates between the free probability regime and this ergodic regime. Okay, we don't understand that much about it, and very little is actually proved. OK, but this is supposed to be like a preview of what happens for the neural networks. OK, so let me just pause for 1 second, because I want to say something neural network related, and how this L over n is really the thing that appears for neural networks as well, though the calculations are more painful, let's say. This OK? Joanna, does this count as random matrix theory? OK, great. I feel good then.
You can do exact computation, right? Because of the spherical symmetry of Gaussians. Like you can write down the distribution of CL.
Yes, correct. Indeed. So I just did. I mean, the direction is uniformly random. Right. And I just told you the norm, and they're independent.
Approximation.
No, oh, sorry. This thing is exact. Right. So this thing is exact. I just did it. And then you can do whatever you want with it, depending on, yeah, right, indeed. But I mean, if the matrices aren't Gaussian, you of course get the same answer. You just have to work a little harder.
So if you would have ReLU, then you would just throw a binomial and get still a formula, right? Because
yeah, at a single input.
yes.
At multiple inputs, it's no longer exact. So indeed. You're right, totally right. Yes, good, excellent observation. Very good. So let me tell you something about, at least at a high level, what the theorems are about these deep and wide neural networks. I spent a long time obsessing over them, so I'm going to share it with you. OK, so here's my model. I've upgraded it back to having a sigma. Not that it really changes much on the slide, but nonetheless. OK, and I'm, again, initializing in the same kind of way that I did before. OK, so there's like lots of papers. Some of them are mine. Some of them aren't. And the main kind of takeaway from these papers is that really this ratio of depth to width plays the role of an effective depth of the network. So if you want to kind of recapitulate the NTK type results, they were in a situation where the depth was fixed and the width went to infinity, so the effective depth was 0. And indeed, you get exactly what happens for depth 0 networks for linear models. That's kind of like a conceptual way of saying it. OK, so there's a bunch of exact theorems, so let me give you some of them. So for example, you could ask at initialization, how close are you to the Gaussian process limit? Well, OK, since you're trying to measure distance to a Gaussian, you should probably measure cumulants. And let me just say that the size of the cumulants is controlled by this ratio of L over N. So if the depth is fixed, you can say exactly how quickly all the cumulants go to 0. But what it turns out is, for example, if you just take k equals, I guess, 2 in this formula. OK, so you look at the fourth cumulant. It's like the first deviation from a Gaussian. Like it goes to 0 like 1 over n. That's OK. But actually, it grows like L over n. So if depth and width are both becoming large, you just don't converge to a Gaussian at all. And that's supposed to be this thing where there's a one parameter family of answers, and only when L over n equals 0 are you Gaussian. That's the kind of philosophy. OK, so similarly, if you're interested in like numerical stability things, exploding and vanishing gradients, if you ask in the appropriate definition of variance, I was a little vague here, what's the variance of the gradients at initialization that you get? Well, in the infinite width limit at fixed depth, you just get this Gaussian process. Your gradients are all order 1. There's no problem. But it turns out that the deeper you are, the larger the variance. And so the L and the N fight each other again, and you get L over N as the thing that controls the effective variance of the gradients. And then you can do other things. You can ask, how close are you to a linear model? OK, so again, you do this at initialization. And for me, a model is linear if and only if the Hessian is 0. I think that's safe. OK, so the point is the Hessian goes to 0 in the appropriate norm, like 1 over n at fixed depth. But actually, it grows with the depth. And they fight each other. And again, it tells you how close you are to a linear. So it's like a meta theorem. That's kind of what I'm summarizing at the top, that L over n is like the effective depth. OK, the only thing I'll say here, and it's going to come up on the next slide in a minute, or in 2 slides in a moment, that if you really want to go to large depth, you can't take a fixed nonlinear function sigma here. Okay, it's like a little thing. If you took ReLU, for example, everything becomes horribly degenerate at infinite depth. You have to do what's called nonlinearity shaping. You have to make the nonlinearity in every layer close to the identity. Then you get a well-defined limit. OK, I'll have a formula about that a bit later. But it's just a kind of disclaimer that I'm not a total crackpot. OK, basically, that's what that is. OK, so I'm saying there's this like second scaling limit where basically what you do is you realize that first taking the width to infinity, then the depth to infinity, causes you to miss lots of interesting things. And it turns out you can take the depth and width to infinity together and ask what happens. And we still don't understand everything that happens, but we understand some things. OK, so here's kind of my basic picture. It's my phase diagram. I sometimes give this talk to physicists, so they like this word, although I'm not 100% sure what it means. OK, that's not true, but it doesn't matter. OK, so again, you have width and depth. And roughly speaking, if the depth over width ratio goes to 0, you're like back in the NTK regime. And this is a stable regime where training proceeds well, but you don't really do any feature learning. And then as the depth over width grows, on the one hand, you're farther from being a linear model. So that sounds good. You could hope to learn some features. On the other hand, your gradients become horribly unstable. And so you don't want the depth over width to be too big. So there's some kind of like trade-off between stability and feature learning. And so maybe being over here is not too bad. OK, that's the basic kind of philosophy. OK, very good. So I told you I like pictures. And you see all the pictures coming up. And I'm not sure what that is. But OK, so far so good. OK, so this is scaling limit number 2, deep and wide. But you'll notice that there are some results about this, at least in a physics level of rigor, that this kind of picture holds if you have a fixed data set size even after training. OK, so I presented the rigorous math theorems I know how to prove, which are near initialization. But if you dispense with all the full rigor, you can do some work and do things after training too, that this L over n kind of controls how far you are away from the NTK answer. But the really sad thing about all these results if I were to be honest, is that there's no data set size going to infinity. Right? Like in the real world, one of the most important practical things is the bigger your data set size, the bigger the model you're going to train on it. That's just like the fact of life. And so if you have 100 data points in a 1,000,000-dimensional space, like I'm not sure what exactly I'm doing other than proving theorems and trying to learn how L and N go to infinity together, which turns out to be useful, but not the whole story. Okay, so that's version 3 of my scaling limit. I want to understand what happens when the depth and the width and the number of data points can all be large. And here there are, it's like the more things you take to infinity, the harder it is to study. And there's not very many theorems in this kind of world. So let me present to you so one theorem came out like last week, and one came out like a year ago. But basically, I'll put 2 theorems into one. So again, you have these fully connected networks. That's the model that you're studying. Just for simplicity here, let me take everything to be n by n. It doesn't matter in the theorems. You can have any widths you like. Okay? But here, I don't know how to analyze optimization by gradient descent or gradient flow. That's obviously what we do IRL, but I don't know how to do it. So what I do is I study Bayesian inference. Okay, so instead of sampling the weights and then doing stochastic gradient descent, I sample the weights. I view it as a prior. I have my fixed training data set, and I have a quadratic likelihood over that training data set, and then I compute a posterior and I ask what happens. That's the version of learning I do. Okay, but the thing that excites me is, I can do this nonlinear nonlinearity. So it looks almost linear in every layer. And then there's this constant psi, which almost doesn't fit on the slide, but is the key thing. And it's psi over the depth times t cubed. Okay, that's like the simplest nonlinear thing that actually gives you an order 1 kind of change at infinite depth relative to the deep linear model. So just trust me that this is the right way to scale the nonlinearity. OK, so what do I know about this model when I do Bayesian inference? So let me say all of this stuff is joint work with Alexander Zlokapas. Many of you know him. He's really amazing. He's a PhD student at MIT. And you should hire him if you can for whatever position you have open, because he's great. I don't even know what he's going to do, but he can do anything. That's my opinion of him. OK, so what do we do? Again, we do Bayesian inference. We take a training data set with p as the number of samples. And we have mean squared errors or log likelihood. OK, so I'll report the results at 0 noise. We have 2 papers. One of them has to take the 0 noise or 0 temperature limit. The other one doesn't, but it doesn't much matter for the theorems I'll give you here. So the first thing that we learned, which I thought was slightly amazing, though maybe some people will think it's kind of obvious, but I thought it was crazy. So if you take psi equals 0, that was the first paper, where you have no nonlinearity. You just take a deep linear network. What we found is that we can exactly write down the posterior distribution you get after training. OK, so if L were 0, if you just have a linear model, then of course, if your prior is Gaussian over the weights, and your likelihood is quadratic, the posterior is Gaussian. That's like what 99.973% of Bayesian inference in practice is based on. But what's kind of cool is that if you have any number of matrices here, you can still exactly write down the posterior non-asymptotically. Okay, and you either hate it or love it, but it's in terms of some special functions called Meyer G functions. But like, OK, that's what exactly solvable models always are. They have special functions in them. So that's really cool. And then in this more recent paper where we take any psi you want, we weren't able to exactly solve the model that you get, but we were able to solve it perturbatively, by which I mean you take the depth, the width, the number of data points to infinity, and 1 over the width is your perturbative parameter. Okay, so you can solve it as a power series and 1 over the width. So that's kind of cool. I was happy about that. OK, so what did we learn? OK, in a sense, this is the main thing I feel like I learned. So after training, there's this one parameter, essentially, this emergent effective depth of the posterior, which now knows about the number of samples that you had. OK, so if you had a fixed depth, you just have p over n. That was the thing from the linear model. That's good. If you have a fixed number of data points, you have L over n. That was the thing you were supposed to get from the analysis I had in the deep and wide limit. And this is how the 3 of them come together in this model. So I didn't know. And I'll draw a phase diagram for you very briefly on the next slide. OK, so that's cool. This is like a new parameter. It's like a thermodynamic variable that describes the structure of the posterior that you get. And I'll explain when I draw the picture why I call it an effective depth. In essence, if you take this parameter to 0, so the number of data points and the depth can go to infinity, but if their product goes to infinity slower than the width, you get something that's completely equivalent to a depth 0, just kernel method. OK, that's kind of why it's an effective depth. OK, so then two more things, and then I'll draw a picture and conclude. So when psi equals 0, if you go back to the deep linear case, what we found is, I think, the first Bayesian kind of preference for deeper networks. So if you're a Bayesian, what you do when you compare two different models is you compare the model evidence. It's like the probability of observing the data under the posterior. And what we prove is that for these deep linear models, the only way to maximize the model evidence is to take the effective depth to infinity. So it's like some very pale shadow of the fact that deeper networks are learning more parsimonious, more interesting features. Okay, it's like a very concrete setting, so I don't want to overclaim, but I thought it was kind of a particularly clean outcome of the theorems. Okay, and then what we learned about the nonlinear models is that when psi is not equal to 0 for general nonlinearity, there's actually a beautiful, I think beautiful, okay, I'm a little biased, but nonetheless, interpretation of what this kind of coupling constant psi is doing for you. It turns out that it is determining the curvature of a manifold into which you're kind of embedding your training data via feature map. And then over that manifold, you're either doing a kernel method at 0 effective depth when PL over n equals 0, or you do a certain data-dependent kernel method when the effective depth is strictly positive. And so it's kind of interesting. It was like the sign of psi determines whether you're in a hyperbola or in a hemisphere, and the size of psi determines the curvature of them. So it's like, you know, I don't know how better to interpret it than just that kind of statement. OK, so let me just pause for 1 second before I go on to the picture. Yeah.
So I'm just curious, you know, in practice, people use different nonlinearities. Like, you know, is there any way to extend this to maybe to ReLU or maybe some LU, CELU, or you know, some other?
So the short answer is this: if you take the ReLU, taking the depth to infinity is a bad idea. Your prior will be degenerate in the sense that every input will get mapped to a random but same output, okay, up to scale. So you have to so this is a reshaping of the hyperbolic tangent, essentially. You have to zoom in near the origin, and that's what tangent looks like. And there's also a reshaping, which I haven't written down, which we don't treat in these papers for ReLU. So I think it's very interesting. We didn't try to redo this kind of theorem for ReLU, but with the correct reshaping, I have every confidence one can do these calculations. It's just, they were pretty painful. I'm not reporting them for a reason, you know what I mean? So I think it's doable, but I don't know what the answer is. I don't know if something qualitatively different happens, for example. Yeah. OK, very good. Do I have time left? Who's the official timekeeper? 5 minutes? Hang 5? OK, let's do it. Sorry, was there another question? Did I see someone? No, it's a phantom. I'm a monster. OK, fine. So let me draw the phase diagram that we draw for these deep linear networks. This is the cleanest one where we have all the information. OK, so again, I'm just reminding you of the model. You have a product of L+1 matrices times x. In the paper, I forgot to say, but it was important given Jacob's question. Okay, we have to take the output dimension to be 1. So this final thing has to be a vector. That's technically what we need to do, and we don't know how to do things otherwise. Okay, we take a Gaussian prior on the weights. And our likelihood is mean squared error over a training data set with p samples. And the regime we're in is everything's going to infinity. The number of samples goes to infinity. The hidden layer widths go to infinity. And because we're doing deep linear networks, we work in a regime where the input dimension is bigger than the number of samples. So you can exactly interpolate your data. Okay, we're doing this at 0 temperature, as I said. So we're only considering posteriors that perfectly fit the data. So you have to have at least some way of fitting the data. And there are these two constants. There was the effective depth of the prior before training. That was this L over n thing. I'm going to call it gamma. And the effective depth of the posterior, p times L over n, which was lambda. Okay, and what happens is it turns out there's basically 2 phases if you want a weakly coupled phase and a strongly coupled phase for these posteriors. Oh my god, that's a gigantic thing. Okay, I have to step back. Okay, so here's the depth and here's the width going to infinity. So in the first phase, what happens is the effective depth of the posterior, which I called lambda, is some constant. Okay, so lambda goes from 0 to infinity. And if this constant lambda is finite, then gamma is 0. L over n has to be 0 because p diverged. So if p times L over n is 17, L over n had to go to 0. Okay, so over here, everywhere, gamma is 0. And what we find is the following. So we find that the posterior depends only on this one number lambda. and on some basic summary statistics of your training data, which I'm not reporting, namely on the number or proportion of directions you actually observed, and on the norm of the minimal norm interpolant. That's the only things that appear in the problem. Okay, so we have an exact formula for the posterior. And then when you calculate the evidence, you can calculate the derivative of the evidence with respect to this parameter at lambda. And you find that it's strictly positive everywhere. That's this theorem I was saying. You always want to increase the effective depth of the posterior to increase the evidence. So the Bayesian's never happy over here. I was thinking of drawing a big frowny face, but it would have been too much. Okay. Even for me. Okay, so this is kind of the first phase, when lambda is between 0 and infinity. And then there's the second phase, and there's a real phase transition, as I'll explain in a moment. And that's the phase where L over n goes from 0 to infinity. So as soon as L over n is positive, P times L over n had to diverge. So everywhere here, the effective depth of the posterior is infinite. But now the effective depth of the prior does what it's going to do. And what you find here is the following. So you had a phase transition in the sense that now the posterior distribution you get is actually independent of the gamma. You get the same posterior everywhere here. And it's the universal posterior that maximizes the evidence for your training data. So it's kind of cool. The posterior completely freezes. There's no more changes in your predictions that you're going to make. However, that's not the end of the story. The evidence still depends on this gamma. So the models you have here are different models, and they have different levels of parsimony, so to speak. And you can exactly calculate what aspect ratio L over n is the best one as a function of your training data. You get some exact formula for it, which I didn't report because it doesn't matter. But what basically happens is, in this phase diagram, your training data always wants to go to deeper networks. The deeper networks turn out to have a low rank bias, which makes them more parsimonious. And then there's a particular aspect ratio which maximizes the evidence. And that's kind of essentially the entire picture of what happens for Bayesian inference with these deep linear networks. Now, I wish I knew what happens for SGD with these linear networks. I don't know if it's only gamma and lambda that determine the asymptotics. Maybe there are other things. I don't have a strong conjecture about it. But I would believe that both lambda and gamma are important in the answer. There might be other things. OK, so let me, I think I'm just in time. So let me just stop. I'm happy to take questions and hear people's comments and all that. Yeah.
Boris, do you have any idea for this nonlinear, like weakly nonlinear model? What class of functions can you learn with this linear sample complexity?
So the short answer is yes. I just didn't report it. I have some idea, but not a complete characterization. So I told you that I do perturbatively things in 1 over n. And so what happens is when p times L over n goes to 0, you get a certain kernel method that's based on this feature map I alluded to. And then the first order perturbation is then a data-dependent kernel method, which knows about the alignment of your training and test points with the covariance matrix of the population. So it's like a kernel method that gets to plug in the actual covariance of your underlying training data. So it knows what directions are more important and less important. So it's like, I have an indirect characterization of what you learn. It's like the things for which your covariance matrices have interesting profiles are the only things that would be helpful. If your covariance matrix is like the identity, you don't get any difference, actually. Yeah, but so it's very partial, yeah.
If your data is isotropic, you're saying that you're not going to do better than a linear.
So in fact, right, so what happens if your data is isotropic, the posterior for the nonlinear things exactly corresponds with the posterior for the linear thing, for the deep linear networks. It just learns to ignore that you have a nonlinearity at all. And OK, that's just how it is. Yeah, I don't know what to say.
Any other question?
So like when you do Bayes formula, you have the posterior is the prior times the likelihood, and then there's a denominator. That's the evidence. So that's like the probability of observing your data under the posterior. And so it's like maximizing the evidence is like maximum likelihood in the space of possible models. That's what it is. So that's why you want to maximize it to kind of determine which model was more plausible somehow for the data. Yeah.
Anyone else? All right, let's thank Boris and all of the speakers.